Case 3. Oh my gosh, where am I? What am I wearing? What if our denominator has irreducible quadratic factors, but none of them repeat? So we're stepping it up in complexity. We have a denominator q of x that cannot be factored. How do I know that? Because in the quadratic formula, I've got my square root of b squared minus 4ac. If that is negative, if this formula is negative, well, that means I'm not going to get real solutions for my quadratic because I can't take the square root of negative numbers and get a real solution. So when that happens, that's how I know I've got irreducible quadratic factors. So what are we going to do for partial fractions? Let's take an example. My example function is going to be f of x is numerator x. Denominator in factored form is going to be x minus 2, x squared plus 1, x squared plus 4. What's going to happen is that each of my quadratic terms gets its own partial fraction, the exact same way that each of my linear terms gets a partial fraction. But where the numerator for my previous two cases is just some constant a that I need to solve for, the numerator associated to each quadratic factor is going to be a bx plus c, or a dx plus e. So some linear polynomial that I would then need to solve for. So I like to remember this, that each of my numerators for a partial fraction has degree that is 1 less than the degree of the denominator. So, right, constant over, I have a constant term over a linear fraction. I have a linear polynomial. I have a linear polynomial over a quadratic, and so on. Now, to put that into action, we might end up needing trig substitution. Right? So this is the reason why we covered trig substitution before we did partial fractions. If I ever see an integral, looks like dx divided by x squared plus a squared, I can tell you right now that this antiderivative is going to be 1 divided by a times the arctangent of x divided by a plus c. Again, if I was writing these slides, I would have written out arctan for arctangent function. Please keep in mind that in Stewart's book, every time we have tangent to the power minus 1, that means the inverse tangent formula. But with this antiderivative in hand, we should be able to calculate these integrals now. Here's an example. The function I want to look at is numerator 2x squared minus x plus 4, denominator x cubed plus 4x. Now, the first step, like any rational function, is to check the degrees. Fortunately, this has already been done for us. The numerator has degree 2, the denominator has degree 3, so I don't need to worry about any long division. Moving on, I'm going to factor the denominator. I see that x cubed plus 4x is a polynomial in which every single term has an x in it. I'll just factor that out, please, and thank you. So my factorization is now x times the quantity x squared plus 4. Easy enough. Now I claim that x squared plus 4 is irreducible. So we need to stop here and use my formula for partial fractions with denominator an irreducible quadratic. Now, I don't just know that because I'm on the lecture slide for teaching how to do that technique. It's a nice hint, but that's not the reason why. The reason why is I know that x squared plus 4 can't have any solutions. Well, first of all, I could do my minus 4ac and compare that to the b squared. But also I know that x squared is a parabola. And when I add 4 to that, I lift it up off the x-axis. It can't have any roots at all. So I have my intuitive geometric reasoning as to why this is irreducible. And if I really wanted to, I calculate my b squared minus 4ac, and I get, well, 0 minus 16. Negative 16 is definitely a negative number. So again, I have another reason why this does not factor any further. I'm going to treat the linear term exactly the way I've been doing linear terms so far. Every linear term just gets a constant for its associated numerator. My irreducible quadratic gets a linear polynomial for its numerator. And where do I go from here? This is the third time that we've done this. I don't expect this to be a surprise anymore. I'm going to multiply through by this denominator, and I will get a nice polynomial equation. Let's take a look at that. So yes, multiplying by x times x squared plus 4. What do we get? On the left side, nice quadratic looking there. On the right side, I've got a times x squared plus 4 because I canceled my x's. I've got bx plus c times an x because I canceled my quadratics. And just like before, I'm going to associate my x squareds together. Here I have an ax squared. Here I have a bx squared. Altogether, I have a plus b copies of x squared. Well, that tells me that a plus b has to be 2. I only have a single copy of an x here. It's multiplied by a c. That tells me that c has to be minus 1. And my constant term here, my only constant is this 4 times a. So if that has to be equal to the constant on the left side, then a must be 1. I guess that means that b also has to be 1. So that's exactly what we're working out here. A plus b has to be 2, c has to be minus 1, 4 times a has to be 4. So the solution is, these are my coefficients. A is 1, b is 1, c is negative 1. Let's write that out. This integral that I want to calculate, the integral of the rational function, is equal to the integral of my rational function written out in partial fraction expansion. So that'll be 1 divided by x. I can integrate that. And x minus 1 divided by x squared plus 4. Can I integrate that? I think I can integrate that. Let's integrate that. So we'll ignore the 1 on x for now. We all know that's going to be the natural logarithm. You better know that's the natural logarithm by now. Now, let's focus on that other partial fraction. X minus 1 divided by x squared plus 4. And actually, we can go ahead and split this up. We're going to split it up at the numerator. So I'm going to integrate x divided by x squared plus 4. That'll be by itself. And I'm going to integrate 1 divided by x plus 4. Do you start to see where that arctangent formula is going to come up? I hope you do. But, you know, we'll also see it on the slide just right here. So the first integral is just going to be a nice u substitution. U is going to be x squared plus 4. Which tells me that a du is equal to twice of an x dx. But I don't have twice of an x dx in there. I'm going to need an extra 1/2. I hope that makes sense where that's coming from. And this third piece that we've broken off here, 1 divided by x squared plus 4. So if I'm integrating 1 divided by x squared plus 4, I must be using my arctangent formula, just like I had. You can rewind the video if you like. My a is going to be equal to 2. So my antiderivative for this part is going to be 1/2. Remember, a is 2. Arctangent of x divided by 2. So all 3 pieces, we can do antiderivatives. For this first piece, I get log of x, natural log that is, with absolute value signs. For my second piece, I get 1/2 the natural log of x squared plus 4. And hey, since that x squared plus 4 is always positive, it looks like whoever wrote these slides has omitted the absolute value bars. That's fine. For the last piece, I get that arctangent formula, just like I said I would. And as usual, our constant integration, we already used capital C, so we will use capital K to spell constant a bit differently. But that's the solution. Now, if we try this again, where we don't have that degree already done for us, we have a little extra work to do. We need to do our long division. So here, I'm integrating 4 times x squared to minus 3x plus 2. That's my numerator. My denominator is 4x squared minus 4x plus 3. So in my long division, I say there's a quotient of 1. How do I know there's a quotient of 1? Because I can get to my 4x squared by multiplying a 1 on my 4x squared. Easy peasy. What's left? Well, I am now subtracting this denominator from this numerator. So 4x squared minus 4x squared is 0. Negative 3x minus negative 4x is positive x. Positive 2 minus positive 3 is negative 1. So my remainder is x minus 1 divided by 4x squared minus 4x plus 3. We can integrate that 1 all by itself. That's great. But now we have a proper rational function. We can try to factor that denominator. Does this denominator factor? Well, no, it doesn't. So my, discriminant, yes, my discriminant formula. What do I have under the square root for my quadratic equation? My quadratic formula, that's going to be b squared minus 4ac, so that looks like 16 b squared minus 4 times a times c. That's going to be minus 16 times 3, which is 48. 16 minus 48 is negative 32, which is in fact negative. Now, discriminant here is a piece of vocabulary that I'm not going to require you to memorize. Discriminant is a special formula. Every polynomial has one. The discriminant formula for quadratics is b squared minus 4ac. All that we need to know right now is that if this formula is 0, the quadratic is irreducible. That's all that it's telling us. It can tell us a little bit more, but that's all we need it for right now. So, what does that mean? My denominator is already completely factored the way it was given to me. It's just an irreducible quadratic. So, how do we do this? My goal here is to use that arctangent formula for the integration. Now, arctangent requires me to have x squared plus some constant squared. So what we're going to do is we're going to complete the square. So this is an algebraic technique. I want to rewrite my formula as some linear term squared plus some constant. The constant I get doesn't actually matter. Here I know that my linear term needs to be 2 times x because I'm supposed to square that and get a 4 times x. The constant term on the inside has to be a negative 1 because I know when I FOIL this square out, I'm supposed to get a negative 4x. Where does this 2 come from? Well, if I FOIL out the stuff in parentheses, remember at this point, I'm forced to pick these 2 coefficients, I'd get a positive 1. I'm supposed to have a positive 3, so I got to stick in an extra 2 there. Now, this is something that you probably saw way back in Algebra 2, and here's where we're going to put it to some practical application for calculus. So I recommend you go back and read up on completing the square, or I'll have some more examples in my future videos. What this is going to let us do is another use up. So let's take a look at this. Here is my integral. with the rational function written out the way it was given to me. Here it is again after the long division step. So I already know integral of 1 dx is x. From the second line to the third line, we're going to use a u substitution. So we're skipping some algebra here. But remember that this denominator is equal to 2 times x minus 1 squared plus 2. So in the u substitution, we're going to say u is equal to 2x minus 1, which is going to be squared in those parentheses. So that's where this u squared plus 2 comes from. I have to make the same u substitution in the numerator as well. So my x becomes a u plus 1. And my du is only worth half of a dx. So that's where this 1/2 comes from. Is that all making sense? So this integral now in u coordinates, we've got to multiply through here, we can pull that out. We're going to have an x on the outside because we already did that part. We have a constant of 1/4. Now we're integrating u minus 1 divided by u squared plus 2. So again, we are going to break this into two different pieces. We're going to take the u divided by u squared plus 2. That's going to be another substitution. And over here, why, this is exactly my formula for the arctangent again. Let's focus on that piece. So this piece right here, my a is whatever the square root of this constant is, right? This 2 is supposed to be an a squared. So in this formula, that's going to be a is the square root of 2. My -4 is a constant that's just coming along for the ride. My antiderivative is 1 divided by the square root, arctangent of u divided by the square root of 2. This middle integral, this poor middle child that I've been neglecting, I can do this with a substitution again. We have skipped the steps. I would say perhaps w is equal to u squared plus 2, and dw is twice of a u du. So I hope that helps it explain why this integral is equal to a 1/8 times the natural log of u squared plus 2. That's our antiderivative here. The final step is to turn all of the u coordinates back into x coordinates. So my x to u conversion says that each of my u's is twice of an x minus 1. I got to square that out. So here I've got my antiderivative is x plus 1/8, the natural log of 4x squared minus 4x plus 3. Then I subtract 1 divided by 4 roots of 2 times the arctangent of 2x minus 1 divided by the square root of 2, all of that plus my constant integration. Now, this is a mouthful, and wouldn't be saying these things out loud to just some random person walking down the street, but we can calculate it every step of the way by breaking down into smaller pieces. And as long as we do it right, those smaller pieces are actually things that we can solve already.